Good day, ladies and gentlemen. My name is Onwuchekwa Daniel, and on behalf of my colleagues whose names are listed, I would like to present our work in progress paper titled Failure Detection in TSN Startup Using Deep Learning. First, I will start with a brief introduction and motivation, then proceed to the aims and objective of the paper, after which I will introduce briefly the time synchronization in time-sensitive networking. I will then present our proposed solution and finally conclude. Time-triggered communication is increasingly deployed for safety-critical distributed applications today. Time-triggered communication systems are suitable choices for a variety of applications in avionics, railway, automobile, and also in the health industry. This is because of the determinism offered by the time-triggered devices. In a distributed system, the operation of a time-triggered devices rely heavily on the underlying synchronization mechanism or services. A failure in the synchronization services can lead to the total failure of the entire system. Fault tolerance mechanisms are often adopted to ensure the safety of the synchronization mechanism. These fault tolerance mechanisms often rely on the global time base to detect failure. However, it is a challenge to detect failures before the establishment of the global time base. Secondly, testing and evaluating safety-critical systems require a large amount of data to get good statistical estimations. This data often can be generated using fault injection. The aims and objective of this work. This work aims at the use of a fault injection framework to generate failure profile data that resembles that of a real system. It then proposes the use of deep learning to classify different failure modes for the early detection of failure before the establishment of a global time base. The generated data is used to train a neural network to recognize the different failure modes. In this work, we would be looking into omission and corruption failure in particular. The time-sensitive networking. It's also known as the TSN for short, and it belongs to a group of IEEE 802.1 standards which cover bridge networks and network management. The standards are shown in the table. The IEEE 802.AS 2011 is a standard for the TSN synchronization services, and this is the work of interest in this work. The TSN synchronization startup. The IEEE 1588-2008 is known as the PTP, which is Precision Time Protocol. It synchronizes the clock of a distributed system. A profile of it is known as the IEEE 802.1AS Rev used in TSN. It is known as the GPTP for short, which means Generalized Precision Time Protocol. Herein, we try to establish a means for early failure detection of the GPTP protocol before the startup process is completed. Our proposed solution herein, usually safety-critical applications are often designed with a very high safety integrity level. For example, the IEC 61508 specifies safety integrity levels in terms of SIL, as in SIL 4 for very high safety integrity level. Now, it is not feasible to gather failure profile data by just waiting for failures to occur, especially in these CL4 systems. Therefore, fault injection is used herein to emulate communication failure modes during startup. A fault injection framework is used where an FPGA is placed according to a cut-through paradigm in the communication system here. The fault injection component is implemented in Xilinx FPGA for corruption and omission. The framework utilizes commercial off-the-shelf components, the NT4E 4-port Napatech adapter to sniff traffic as in over the network. The framework has the capability of generating a huge amount of dataset that captures the startup behavior for a given physical setup. The generated data is then used to train a neural network to identify failures before the TSN startup process is completed. The conclusion. Deep learning is considered as a suitable choice due to the lack of domain understanding for feature introspection required to use the data generated by the fault injection framework for fault diagnosis. This generated data, that is gotten from the fault injection framework, can be used to train a neural network to identify failure on every startup for a given physical setup. Future work will gather experimental results to train a deep neural network. Thank you very much for listening.